Okay, so good evening, everyone. Uh, so did everyone give that mock test scheduled on 8th March this week?
No, sir, I had classes.
Oh, so you didn't give in any of the shifts. The There were
No,
two
sir,
shifts.
actually, no. Yeah, sir, I have classes from morning 9 to like evening 5. So both of them are overlapping.
Okay. I will tell Shankar to arrange for another set of mock tests on weekends. Okay.
So
Uh,
if the mock test papers are posted on WhatsApp, it will be nice, sir. Like for this one.
okay, I will try to get hold of the mock test. Actually, it's not set it up by me. It's either by Shamprit or I don't know who was in charge of setting up the paper. By the way, how was the test? I mean, those of you who gave that exam, was it difficult, easy, lengthy, or something? Anyone? Okay, so let's start the class, never mind. So today let's practice some problems. So problems. Is it writing? So let.
Sir, I have a
Okay.
request. Can you arrange a mock test online, like a proctored one? Cause I'll be leaving for my university next week, by the end of next week.
Okay, so you mean offline classes are starting from next week, right?
Yeah, sir. So I have to
Actually,
leave.
whenever I schedule a test online, most of them either don't submit or like submit it over time. So I don't think that online exam has much of a utility here. So okay, I will try to schedule an online exam next week or the week after that. Okay. Okay. So the problem. So let g be a differentiable function. I mean at least once. So C1 means it's differentiable and its derivative is continuous. And also assume gx naught is equals to 0 for some x naught in R. This is condition number 1. Condition
So
number 2
C
is
exclamation means. So C exclamation means.
it's not exclamation, it's c to the power 1 you can say. And that's full stop. I mean, yes. So C1 in general ck of some interval. Here it's over the whole real line. This means the function. So if f is inside ck of some interval or some set, which implies f is k times differentiable and the kth derivative of f is continuous over that particular interval in whatever is here, maybe some interval d. And the second condition is g dash x naught is greater than It's not x naught. G dash x is greater than x gx. And just a minute. Okay, so this is the problem. So gx is some function, and it cuts the x-axis at some point x naught, and g dash x is greater than gx for all x in R. For over the whole domain, gx is less than its derivative, and we have to show gx is positive for all x greater than x naught, and equivalently gx is negative. I mean, this is not and this is for all x less than x naught. So how to proceed? So to utilize this bit of information, since we know that for any function of the form e power of x, let this be hx, then h dash x will be e power of x times fx minus fx plus f dash x, right? Similarly, if we make it no, not minus here, e power minus x, this would be minus fx plus plus f dash x. So then we will be able to use this information. So we define hx equal to e power minus x times gx, and equivalently differentiating it, we get e power minus x times g dash x minus gx. Now, since given g dash x is always greater than gx over the real line, we have this is always positive. I mean strictly positive. And this is already positive, right? So the whole thing is positive. So implies g dash x is strictly positive, or hx is increasing. This implies like h has to be of the form this, right? And we know x naught is a point of intersection of hx with the x-axis. So and observe it has to intersect somewhere at with the x-axis, since other else, because like if we check the limit x tends to minus infinity hx. So what happens when you so e power minus infinity is e power plus infinity, that's infinity, and And about gx, we don't need that. Anyway, so this will be minus infinity, and limit x tends to my plus infinity, x would be plus infinity. I have to show gx. Okay, so now it's obvious. This is the point of intersection with the x-axis. So anything onto the right of x naught will have a positive value of gx, and anything to the left will have a negative value of gx. So it's more or less proved. So moving on to the next question. So let a be some positive real number, and we have to show the equation 1 plus x squared by 2 equals a times e power x has a unique real root.
Excuse me, sir. In the first question, it was given that G is from R to R, B C1. That means it's one time differentiable. So that shouldn't be a straight line.
No, like it's at least once differentiable. It can be more than that. To solve this question, you don't need more than one differentiability. So that was the bare minimum that was stated. Like this definition just means uh, like x squared is c1 too. So x squared is actually c2, but c2 is a subset of c1. So x squared is c1 also.
Okay, sir.
So what about this one? We have a polynomial on the left and a exponential on the right, and what are the roots? So something like this. I have to show it has a unique real root. That is it just touches the exponential like that. So we can work with the difference function. So let's define gx equal to e power x minus that polynomial. What's a derivative? So power x minus 1 minus x. So now g dashed x. if we subtract the 2, then gx minus g dash x equals minus x squared by 2. Right, so that's negative for all x inside R without 0, which implies gx is again less than g dash x. And from the first problem, if gx is less than g dash x, and like g is already c1 here, just, which implies there exists x naught in R such that gx naught is equal to 0, and gx greater than 0 for all x naught, or for all x greater than x naught, and gx is less than 0 for all x less than x naught. And that gx is exactly our solution, since gx naught is, this implies a power x naught minus or equal to 1 plus x naught plus x naught squared by 2. Right, so if you increase the value of x to something more than x naught, this thing will, so then gx naught will be greater than 0. Right, so then this increases, so this increases, and if you decrease the value of x naught less than x naught, then this decreases. So they will never be equal anywhere other than x naught. Okay, so next question. So let P1, P2 up till Pn be a finite sequence of real numbers such that the sum of 2, 1. Alpha is some real number greater than or equals to 0. Alpha is not equal to 1. H of alpha is defined to be 1 by 1 minus alpha times log of the weighted, this um, like pi power alpha, sum over pi power alpha. So evaluate limit alpha tends to 1, H alpha, and show that dh alpha by d alpha plus 1 minus alpha squared. Oh, sorry, actually, this is alpha, not a. Some weird looking thing. We have to show that this weird looking thing is true. And what is Zi? So Zi is pi alpha of sum over j equals 1 n. EGL. And also the last part, hence or otherwise, show that H alpha is non-increasing. That is, it's either flat or is decreasing function of alpha. This is so that wait for a few minutes. So what is the limit? I guess it would be easier to multiply with H alpha equals 1 by 1 minus alpha times log of, uh, which implies, let's define some F alpha equals 1 minus alpha times H alpha. That equals ln of that sum. Therefore, if we try to find that limit, alpha tends to 1, H alpha is equal to F. Uh, so it's limit alpha tends to 1, F alpha by 1 minus alpha. And okay, here we have a crucial observation. Since so let me, since sum over pi power 1 is equals to 1, this implies f1 is 1. There, sorry, f1 is log of 1, that is 0. So we can add and subtract f1 here. So like we don't even have to subtract, we can just add or subtract. So we have alpha minus f1. Alpha is going to 1, so 1 minus alpha is going to 0. This is equivalent to limit h tends to 0, h alpha 1 minus alpha is h. So that is 1 minus h is alpha. 1 minus h minus f1. Or we can just negate it or find the it's the same thing. Since h is anyway tending to 0. So this is f dash 1. And since this function is already differentiable, f dash 1 is pi power 1 and pi ln pi. A power x, and the derivative of a power x is uh, a x ln a, right? So ln. So 1 ln pi. Sum over I, right? Denominator goes to 0. It's just sum over pi ln pi. And can we
So is it sum over whole here? Sum over whole into pi ln pi? I mean pi ln pi whole sum over.
just a minute? I can't hear you properly. Wait, that's
Can you hear me now, sir? Hello? Hello?
just a minute. Let me reconnect. I mean, move out of the video and rejoin. I'm having some issues. System. Hello, am I audible now? I mean, someone please say something.
Hello, sir. Am I audible now?
Yeah, yeah, you are audible now. So
So
what
I was
was?
asking that. I was asking that is it a whole sorry whole sum over of pi lnpi whole the
Yeah, yeah,
numerator.
yeah. So we are differentiating ln of sum over pi power alpha. So that is the denominator is right, like it's just sum over pi power alpha, and the numerator is sum over pi power alpha times ln alpha, ln pi, right here. So this is sum over the whole thing. So sum over of pi of ln pi by sum over of pi. This goes to 1 and the numerator is retained. I don't think we can simplify it further, so that's our answer then. Sorry, I should have used the purple ink. So now the next one. So dh by d alpha. We have to show this. Okay. So if we try to differentiate this equation, 1 minus alpha h alpha. So differentiating, so minus h alpha plus 1 minus alpha times h dash alpha equals, so 1 minus alpha times, so these are zi's.
Sir, didn't understand the ZI one part.
Uh, no, let me differentiate the original expression of hx or h alpha. So this was, then h dashed alpha is minus 1 by 1 minus alpha squared times minus 1, so it's plus 1. And this is sum over pi alpha, pi plus, so this is what we are getting with. Okay, so now zi, from the question it was defined zi is to be pi power sum over pi power alpha, right? No, there was an alpha there. Yeah, so we can take this sum over, so then the second term becomes, so this thing becomes, is it clear now? I think so. What else to show? This is zi. Hmm. So let me take 1 by 1 minus alpha squared common. So log of some summation plus 1 minus alpha times sum over zi ln pi. Just a minute. Observe that sum over items from 1 through n. Zi is sum over pi power alpha by sum over pi power alpha. This denominator goes to 0, so it's equivalent to sum over pi power alpha. No, just a minute. This only goes to 0 for alpha equals to 1. I mean, okay, we don't even need that. So it's sum over pi power alpha by pi power alpha. So it's 1. So sum over zi is 1. Uh, so that means we can bring in zi anywhere in. So where should we try to bring zi? So let me try approaching other way around by simplifying this expression. So this holds if and only if h dash alpha equals. We already have this term here with the 1 minus alpha, and So minus alpha times that thing. So somehow this thing must be equal to minus alpha times ln zi ln pi plus ln sum over pi power alpha. How is that even possible? Hmm. Sum over zi is simply 1, right? Wait a minute. Why did I multiply with zi? Can I do that? Oh no, it was there. Okay. So I can multiply this with sum over zi since they add up to 1. Zi is that weird thing. This is a constant. I can get it inside the summation, right? This, okay. So does that mean I can take zi common? This is alpha. And that proves our claim, since this thing inside the argument of log is zi. So it's minus of sum over zi ln zi. And that's exactly the second term. Do I need to write it out clearly step by step, or is this okay? Like these are all if and only if statements. I'm just working with the second term inside the brackets. So if and only if minus sum over zi ln zi, which is true, right? So it was just plain and simple algebra, nothing more. We are left with the last part. So show that h alpha is non-increasing function. So 1 minus alpha squared times h dash alpha from the previous one. This is sum over zi times ln pi by zi. Okay. Yeah, so this is from part B. Now we have to show z dash alpha is non-increasing, so we have to show it's less than 0. How to proceed? So ln x, this looks like this, and so logarithmic function is slower than the function x equals to y. I mean x equals to this function, y equals to 1 minus x. Sorry, not this one, x minus 1. So what is the Taylor expansion of 1 minus x? To simply find that, let f(x) equals to log 1 minus x. This implies f(0) is 0. F dash 0 is it's minus 1 by 1 minus x minus 1. F double dash 0 is 1 by 1 minus x squared minus 1. So it's again minus 1. Just a minute. Yeah, it's minus 1. So we have Taylor's expansion. Zero times x plus f dashed 0 times the 1 factorial times x plus so on minus x is squared by 2 factorial, x cubed by 3 factorial, so on. So if we just take the first one, we get ln 1 minus x is can I say? Ln x squared, x squared by 2 factorial. This is a purely negative quantity. So negative something. I'm adding something negative. So this must be more. So now let y equals to 1 minus x. So log y less than or equals to x is 1 minus y. So minus of 1 minus y equals to y minus 1. So that shows ln y is less than or equals to y minus 1. So now we can use that inequality here to say, therefore 1 minus alpha square h dash alpha equals sum over zi ln pi power alpha by zi, sorry, just pi by zi. This is our y, sum over zi times pi by zi minus 1, which is equal to sum over pi minus sum over zi. Sum over pi is 1 by our, that was given, and we showed sum over zi is also 1 somewhere here. Right. Since sum over pi equals to sum over zi equals to 1. This means this is 0. Therefore 1 minus alpha squared h dashed alpha less than or equals to 0, which implies h dashed alpha. Since this is a positive quantity, it's less than or equals to 0. H dashed alpha is non-increasing. Okay, is that clear? So that proves the last part.
So after ln y less than equals to y equals to 1, I didn't note. Could you please show? Okay, sir.
After this step, I mean,
Yes, sir. Done, done.
hmm, Q3. So this says find the area of the largest circle centered at origin, which is inscribed between the graphs y equals to 1 by. So find the area of the largest circle inscribed between the graphs y equals to 1 by 1 plus x squared, y equals to minus 1 by 1 plus x squared. So how about this one? do the graphs look like? Because that's what we have to like figure out using calculus. This should be just plain geometry and intuition. So try it for a few minutes. Okay, I forgot to mention one data. Largest circle centered at origin. So centered at origin. Now it's okay. Okay, so how does the graphs look like? So y equals to 1 by x or 1 by x squared should look like a rectangular hyperbola. So that should look like this, which means, so if we add another x, that gives us, so at
So the
0
graph will
this
look like
is,
A and V respectively, like a
uh,
curved A and curved V.
curved a, I mean this a.
Except that strike in the middle. Yeah, curve it a bit. The edge will be sharp at zero. X equals to zero.
Curved b, you mean like this? Okay, let me check. So at y equals to 0, this evaluates to 1.
So V means just the reverse of A.
Okay, right, that is obvious since this is just negative of that graph. So it would be symmetrical about the y-axis. So if it is something like this one should be something like this. But we don't know any of them now. So 1 at 0, derivative at 0 is 1 plus x squared, which is 0. Okay, so it's flat. Now x tends to minus infinity, y is 0, since its denominator tends to plus infinity. Similarly for plus infinity, y is 0. And what about the concavity and convexity? Observe that y dashed 0, I mean y dashed x equals to 0 has only one root, one real root, right? So we can expect this point at origin to be either a maxima, a global maxima, or a global minima. But it seems like it would be a global maxima since at either ends it goes to 0. For the concavity, y double dash x is derivative of 2x is 2 times 1 plus x squared, 2x
So
plus,
by in convex functions, the curve faces towards the x-axis, right? So this is a
this is
convex, now.
this is convex, this is concave. Just think of
So
a
sir,
real cube
then
and the entrance looks like concave downwards, so this is called concave.
yeah, sir, and then these functions are convex, right?
No, we don't yet know that. I'm just calculating the double derivative for just that. So, yes, 2x minus 2x times 1 plus x minus 2x. So it's minus 2 minus 2x squared plus 4x squared. So it's 2x squared minus 2. And the denominator is always positive. We don't need volume. So this This shows there. This changes convexity at plus minus 1. So this is plus, plus minus plus. So before this is 1, this is minus 1. So after minus 1, this thing is positive. So double derivative is positive. That means it is convex. Okay. So up till 1, this is convex. After 1, this turns concave. This is, what is the value at 1? So y1 is half, I believe. Y minus 1 is also minus, no, y half, it's also half. Okay. So this is half. This is convex. And then it changes convexity to be concave. It continues to be concave here, and then again it becomes convex. Should be something like this. And since the other one is just its reflection, should be like this. This. Okay. This is minus half. So a circle has to be something like,
So how did you get that the curve becomes concave after between -1 and 1?
yeah, so y double dash x has an expression like this one. And now you can use a wavy curve method to see in which region it is positive and which region it's negative. So from plus infinity
Okay.
to plus 1, it's plus, and then minus, between minus 1 to plus 1, it's minus. That is, uh, it's concave there. So here it's convex, convex, and here it's concave. Reverse is true for the this function, y equals to minus 1 plus x squared. So I don't now. Okay, so to find the largest radius of the circle. So what is the distance between origin and any one of the curve? So this is d. D equals to square root of 0 minus x squared plus 0 minus y squared. So it's x squared plus 1 by 1 plus x squared whole squared. So we have to maximize it, right? Oh, sorry, it has to inscribe, right? We have to minimize it. So we have to minimize it. So here d is a function of x. We can directly differentiate d now to minimize it, but I guess we try to simplify d first. So d is minimum if and only if we can square it first. Since square root is a strictly increasing function, this is minimum. and only if, now obviously this d has to be something positive, and x square is a graph like this. So right in the positive region, x square is also increasing. So we can let go of x squared, right? Right. Okay. So we have to minimize it. No, we can't let go of x squared, I believe. Okay, let's differentiate it directly now. So just call this some h or something. So h dash x equals to 0 and only if 2x minus 1 plus x squared whole cube minus 2 times 2x. So assuming x not equals to 0, we can cancel out 2x. That leaves 1 plus x squared whole cube equals minus 2. Okay. So cube root of minus 2. No, it's cube not minus 2 is plus 2. So cube root of 2 times, so 1 plus square root of that is x. Yeah, so that's our answer. So therefore, max radius of circle is x equals. You can even find the points at which uh, this circle touches the functions. So obviously f0 is 1, which is like, I believe, just a minute. Yeah, 1 is greater than square root of 1 plus, is that? Yeah, this is, no, just a minute. No, sorry, right. This is 2 minus 1. Can't be more than 1, right? Since then, it will only obviously be outside this 0 comma 1 point. Yeah, so 2 square root of 2 power 1 third minus 1 is less than 1. So that means our circle will be something like this. The graph will be something like this and this. Okay, now moving on to the last question. So f is a function from closed 0 pi to r. It's differentiable. So f is also c1 in 0 to pi, and uh, there doesn't exist x in 0 pi such that fx is equal to f dash x equals to 0. Okay. and we need to show S the set of all those x's where fx equates to 0 must be finite. Try this one out for a few minutes. Okay, so any breakthrough? Hmm. We will try to prove it by contradiction. So proof by contradiction. So let's assume S is indeed finite, indeed infinite. So that implies we can take any sequence. So there exists a sequence xn inside S such that all xn's are distinct. That means xi not equals to xj for all I not equals to j. Now observe that S, the set S is bounded since it's a subset of the domain, and the domain is 0 to pi. This implies the sequence xn is bounded above by pi. So by, what was the name of the theorem? There was some name. Okay, I forgot. So in any bounded sequence, since in any bounded sequence there exists a subsequence such that xnk, let xnk be the subsequence, k is the running variable, xnk is convergent. Okay, so that implies there exists the subsequence xnk. Okay, that was the statement of the theorem, so I'm writing the implications here. So this is convergent. Again, for simplification, I can rename it as yk maybe. So now uh, for all y, okay, so it's convergent, right? So let's say it converges to some limit L. So limit k tends to infinity, yk equals to, so let this limit be L. Now L is inside S, which implies FL is 0. That's the definition of S. This also implies fyk is 0 for all k in naturals, since each of them are inside. They are a subsequence of xn, and xn is a subsequence inside S. Sorry, is a sequence drawn from elements of S, which all have that property that y of xn is 0. Now, see that this limit. So since f is continuous from the definition, so from definition we have fyn goes to fl or converges. So whenever we have a sequence of xn that converges to some finite point x, the sequence of continuous functions of xn also converges to the function of that limit. Right, that was one of the three definitions of continuity. So this implies limit k tends to infinity fyk equals L, since fyk, this sequence is convergent by continuity of f. But we know one thing, we know this is a zero sequence. This sequence is zero, since all the terms of this sequence are zero, which implies L has to be zero, right? Sorry, not L. I mean FL has to be zero. So the limit is indeed zero. Okay. Now to arrive at a contradiction. So, so what is f dash x? Its limit, it tends to zero. Right, it can be also written as limit n tends to, or k tends to infinity, maybe. K tends to infinity. Mod or anything, y minus yk. No, sorry, not y, L minus yk. F of yk, f of L. This is yk minus L. Since h equals to yk minus L goes to 0 as k goes to infinity. From our assumption that x n's are all distinct, we have a yks are all distinct. Hence, this limit is always well defined for all values of k, since yk is never equal to L. It's the limiting point, so right. But the numerator is always zero, since yl is since fl is zero and f of yk is always zero, since all of them are in s, right? Equal to limit k tends to infinity, 0 by some non-zero quantity. It may be small, but it's non-zero, which is equals to 0. So f dash x is 0. I mean, this is not f dash x, this is f dash L. So this is f dash L. Therefore, we found L inside the sequence. I mean, sorry, not sequence. L inside the set S. Sorry, so we found this limit. The limit point is inside the set. If you ask why, then that's because, just a minute. Okay, anyway, so we found L inside S such that FL equals to F dashed L equals to 0, which is a contradiction to assumption that, no, not assumption, which is not possible from the given condition, right? So this is a contradiction. So hence F, not F, S is finite. Now, as of why L should be in S, let me think. So, what is L? L is the limit of a subsequence, and the original sequence xn was bounded, right? Can we claim S to be S? That only happens when S is closed. How to claim S is closed? Uh, Actually, there is a theorem, I don't know if I mentioned or not. So this S is actually F inverse of 0, right? It's the zero set of F, also called the zero contour of F. And this zero is closed, right? So the theorem says that uh, the inverse of a compact of a what do you say, a compact set, zero is a compact set. Inverse of a compact set with respect to a continuous function is compact, and compact here in finite interval means closed. So S has to be closed, which forces L to be inside S. The limit of any sequence in a closed interval is inside that interval. I don't think I can explain it further, since then I have to prove this result, which isn't like, there's a lot of other things to prove before we can arrive at what is the definition. Oh, I guess I defined what is a compact set, right? Yeah, I defined them. So like 0 pi, this is a compact set. A finite set like 1, 2, 5, 7. This is a compact set. And this is not a compact set. A compact set just means like if you have a collection of open intervals such that each, so you have a set A, right? You have a set A, a subset of real numbers, and there exists some a sequence of intervals. Alpha in some index space V. So there exists a sequence of intervals. All the intervals are open in, so this is inside tau r. That is the topology, or what do you say, the set of all open intervals in R that I call tau r. Okay. So I alpha, each of the I alphas are open intervals in R. So there exists a sequence of such open intervals such that union over all those intervals. So A is a subset of the union over all those intervals. Now, there exist, this is for all. So for all sequence of open intervals may not be finite, may be arbitrarily large sequence such that their union contains A. Now there exists a subsequence. Oh, sorry, there exists finite subsequence. So there exists uh, is it finite? Yeah, it is finite. So there exists alpha 1, alpha 2 up till alpha n less than infinity, such that A is inside union over I run inside 1, 2 up till n. I alpha I. So basically, we call this union over alpha I, union over alpha, a cover of A, and this is a subcover. That is, we are taking few of the intervals and leaving out infinitely many of them. It's called a finite subcover. So then A is compact. It's just a new term to describe this property. So by this definition, you can see that any finite element set like 1, 2, 3, 4, these sets, you can define any sequence of open intervals like any. Some may be 1, 0 to 1, 0, 1, 2, not open. This is not open. So like this is the number line. You can take this interval, then this interval, then this interval, then that interval, and again the whole interval, and you can go on sequence of intervals. And you say this is a cover of this set, this set A. Then I will find a subcover saying that I will just take this interval. No, I will just take the last interval. I mean, not the last, the fourth interval, starting from this to this. I don't remember if I gave a proof for this. This is called the Heine-Borel theorem, which says that any closed bounded interval is compact, which makes all these in intervals, these are closed and bounded intervals as sets compact, which makes zero compact. Where is it? Which makes this, not this zero compact. And f is continuous, which implies f inverse, if it exists, is continuous. I don't think so. Okay, so let's not. Like it at least implies f inverse is compact, and compact implies bounded, closed and bounded. Closed and bounded implies every sequence has its limit inside that same set. So L has limit in S. Since S is a closed and bounded set, since S is f inverse 0, and since 0 is compact. Okay, so that was a mouthful. It's almost time. Let me. So let me share a few problems on, say, suppose. So how about graph theory? Okay, I'll set just one problem. So I discussed graph theory once, I guess 2 or 3 weeks ago. Just discussed up till what was subgraph and induced graphs and all that. So it's this question says if, then I have to define what is a matching. Okay, to keep it simple, no, I can't keep it simple. So graph, as you know, is a pair of It's an ordered pair of the edge list. First comes the vertex list and an edge list. But edge list, where edge list is a subset of the Cartesian product of vertex list with itself. And this is for simple directed graphs only. Sorry, undirected graphs only. So it may not be connected, like it may be something like this. So now the question is, so let for like the number of vertices in the graph be n. So find kn is the complete graph with n vertices. That is the complete graph, for example, with 4 vertices is this thing. So every vertex is connected to every other vertex. So this is called a complete graph. We denote it by Ka4. K3 is triangle. And K5 is a pentagon with all its diagonals. Right. And similarly. So find the number of trees in uh, Kn. So what is a tree? A tree is a graph such that it doesn't have a cycle, nor does it have a. So a tree is a graph without any cycle and is connected. That is, you have to. There must be a path from any given vertex to any other vertex. Maybe direct, maybe indirect, but like in this case, with the 4 vertices, this is a tree, this is a tree, this is not a tree, this is not a tree since it has a cycle, and this is not a tree since it's disconnected. There is no path from this vertex to this vertex. Okay, so I guess you got a kind of intuitive idea what is a graph. So yeah, that's what is a tree. So you have to find all possible, or the number of distinct trees in a complete graph. Number of distinct subgraphs which are trees in a complete graph. So basically you will have n points. You have to join them in such a manner that there is no cycle and every point is utilized. So that's all for today. Okay then, thank you and good night.